from UC Riverside, and I believe the speaker will be Xiaofan soon, but let's see.
Hello everyone, thank you for joining us today. I'm Xiaofan from UC Riverside. Today, I will be discussing shapes and summaries for risk detection in concurrent data structures. Firstly, let's talk about concurrent data structures. Those are data structures that can grow and shrink as needed. Most are node-based. They are used to synchronize states in parallel applications. They can be excised and changed simultaneously. Here are some common ones used in parallel applications: skip list, replace a priority queue or a map; linked list, used for concurrent queues; AVL tree, used for maps and union sites. Implementing those data structures correctly is tough due to concurrency bugs, especially data trees. So we want a technique to help us automatically find bugs in multi-threaded programs. One powerful method is Concolic testing. Comparing to random tests, Concolic testing uses symbolic inputs and a solver to solve the constraints to excise their paths, which gives a more reliable result. Here's a quick review of how it works. First, user needs to specify some symbolic inputs as the selector will select the path pi, and the execution of path pi on S gives a symbolic constraint ci. The constraints are collected from branch conditions along the path pi. Then the constraints ci are sent to the solver when we need a concrete value to run some functions, or we need to reduce execution complexity. It will solve the concrete input I for symbolic input S and send to the executor. Finally, the bugs are reported if it has, and it moves to the next iteration to test path pi plus 1 using random or the first order until all user expected passes are tested. Then I should bring up an important concept: data shape in pointer-based data structure. It consists of pointers and the memory objects they point to. Why we care about data shape? We first meet the problem that one data structure shape cannot cover all paths. Let's consider a case where we want to expose more paths in programs with concurrent data structures. For example, we assume S is a global object, global variable. In thread 0, there are two reads that happen in two paths with thread 1, both right reads. However, if we see the condition of those two paths, one requires next pointer equals to null and another null. So we have to use two different shapes to expose the reads. Only one shape can only expose reads 1 or reads 2. You can never expose both using one single shape. Manually find those shapes are hard, error-prone, and tedious. We wish to automatically generate shapes to excise different paths. Now, let's discuss the performance issue. We want our system to explore the shapes efficiently, but there is redundant work if a function is called multiple times. For example, if there are m paths from the main function to foo is called m times, generating m shapes. Each call inside foo needs shape generation 2, let's say producing n shapes. So we ended up with m times n shapes, leading to a loss of redundant work. Can we explore the shapes just once for each path in foo? Consider this example with function foo and min. In the min function, node n and user input argc are symbolic. For path A, we assume it will call from the main function and take the true branch. The left figure shows the final shape for path A after calling foo. The second figure shows the date shape is another path B, you can find there are lots of similarities in the generated shape because we call the same function. The shape growth in full is independent to the main function. If we can find the product shape generated in the function full and make a summary for shape, we can greatly reduce the redundant work in shape exploration for next time calling the same function. Okay, let's do the next summary construction. To create a function summary, we run the full function before starting test. We call this step Concolic unit testing. In unit testing, the parameter a passed in is a symbolic pointer. The data shape will expand when pointer is dereferenced and related constraints are collected. Here in this figure, we show what the shape infer for path 1 looks like. The shape will expand when date field is dereferenced in node A next pointer. So the node N0 is created and date equals to 0 has been set there. Then if we have a branch in the function, we need to generate different shapes for those paths. We will use a decision tree model to select which shape to use. So the condition is collected during unit testing. For example, a arrow next not equals to now in this example. This is a key idea how to summarize a function and make the generated shape can be reused in the future. However, decision tree cannot be too deep. So if there are loops or complicated control flow graph, only the top levels could be summarized. Other parts will fall back to the original function call. If there are function calls, like adding a function bar here and call this function, we can isolate the side effects that function bar are made. Assuming no global variable size, only the date shapes passed in and the return value are affected. So we reset the shape to symbolic pointer with unknown and create a symbolic value as B for the return value B. Following branch must be resolved again due to those side effects. Even its previous condition a next or not equals to none or true, but you could see we still need to evaluate both of those cases because we didn't know the side effect. After introducing the construction of the summary, let's have a look at this example to see how the summary is getting invoked if we give a summary of function full and an input shape. Let's use this example in path A is taken in the main function. Okay, so we have to follow the decision tree model. First, we evaluate the branch condition from the root node of decision tree and quickly reproduce for both branches. For the true branch, we meet a function call for the bar, and we will receive call summary invocation method for function bar here to produce a result shape. If it's summarized, or if it's not, then we just simply run it. Assuming it will return to variable b and I change number 0 to 1 in the data field of the last node in this shape, like this is highlighted shows. The modified shapes will be used for the following steps and map back to the pointers in the summary. Here we map back the shapes and use the return shapes in the following step. And this branch condition should be evaluated again using the returned shapes and producing the final result. Now we know the branch should take true and corresponding changes to the shape presented. After we really made those changes to memory, all side effects in the function full are reproduced. The data shape should be returned to color. This is how we invoke a summary. To make the system can detect traces effectively, we desire a two-stage solution. Concolic unit testing is running before the testing to run each function individually and produce the summaries and use the log-side approach to detect potential risks. Then in the concolic testing of full program stage, we will start testing from main function and confirm each race is really happening and use the summary to speed up it. We can compare the normal function call with summary invocation. First, both of them should evaluate the branch conditions, but then once we need to generate the data shape, inside the normal function call, we have to collect pointer constraints. We have to call solver to solve the shape and handle all memory access. Doing some invocation, we skip those work and directly get the generated shape from memory, which is the cached result, copy the memory object, and the shape is generated and suitable for current SSRD. This is much faster than keep generating shapes for function call. In addition, only non-local memories access have to be handled since all local memory size is already reflected to the memory object in the data shape. Next, let's talk about experiments. To evaluate the effectiveness of rate detection of SSRD, we made a few benchmarks by eliminating synchronization operations from open source programs, including skip list, unrolled linked list, priority queue, and AVL Tree. We compare our approach SSRD with a baseline approach, Cloud9, which is the one we built on top of it. This is a symbolic execution engine, supports multithreading. Give each program an initialized date structure and used to run the test case for Cloud9, but we will ask SSRD, our approach, to automatically generate data shapes to test them. In this figure, we can see the blue shows the number of rays detected in each benchmark using SSRD, comparing to the light blue Cloud9 one. Almost all benchmarks is getting out. However, this is due to the ability that's exploring data shapes. You will find much more paths are taken. If you see the yellow line and the orange line, the yellow line shows the number of paths explored using SSRD, which is much more than the orange one, which shows for Cloud9. So the cost is much more slower. However, with the number of paths increasing, it will take much more time to run those test cases. Many complicated programs may take too much time to get a meaningful result. Summarization is a way to reduce the time required. Please see this table. It shows without using summarization how much time will taken in those test cases. Since summarization requires an additional summary construction time, this time is also listed there. Then, if enabled, how much time has been reduced? If we see the first line as an example, it says skip this test case running insert function without summarization. It takes 320 and 26.56 seconds without summarization. But it cost 172.3 plus additional 0.1 seconds for summary construction time. So it becomes much faster. The reduction time have been 47% of the total time. In the parentheses, we list if we didn't consider the construction time, how much time will be reduced, which is 47.2%. In those benchmarks, there is a still case getting worse when enabling summarization. We look into it and find the reason is the decision tree is not deep enough to cover the path. Each function can be described as a control flow graph, but decision tree model is not able to cover very deep path. If that happens, it may hurt performance. Even though there are cases not covered, we could still see in the most cases, summarization contributes a lot for for this system efficiency. It's a high-performance cache mechanism for frequently used paths and quickly reproduce the shapes. It gave us a way to find databases both effective and efficient. Okay, that's all for today. Thanks for listening.